Now we continue our mini conference, Skorokhod readings for a young scientist in probability and stochastic process theory. And it is my pleasure to announce first speaker today, Ulises Perez Centeis from National Autonomous University of Mexico, with a talk, a stochastic flow representation of one-dimensional diffusions. Please.
Okay. Hi to everyone. Let me share with you my screen. Okay. Hi again to everyone, and I want to thank the organizer for letting me be here. And today I want to talk about a stochastic flow representation of one-dimensional reflected diffusions. And this is a work in progress with a friend of mine, Gerardo Perez Suarez. And I would like to introduce myself a little. I am a PhD student at the National Autonomous University of Mexico. You probably don't know National Autonomous University of Mexico, but I can show you a picture of it. And this one. This is one of our main buildings in our university, and I like very much because it has a reflection here. But okay, let's move on. Okay, first, to fix ideas, I want to recall you three basic construction of reflected Brownian motion. The first and maybe the most intuitive one is this. You have a Brownian motion and you just take the absolute value of the Brownian motion. So what this path transformation does is you have a Brownian motion, it has positive excursions and negative excursions. Then you look at the negative excursions and you just reflect them to make them positive. And then we have our reflected Brownian motion. It's very intuitive and very natural, I think. And there is this other construction of reflected, okay, this here has to be B. There is this other construction of reflected Brownian motion, which is made by a time change. What you do in these constructions is, once again, you look at you have positive excursion, you have negative excursions, you look at the negative excursions, but this time you disappear them. And then you just put together these positive excursions. And once again, you have this object that coincides with the previous one, and here is a reflected Brownian motion. And the third and the last and the most important for us is the following construction. Once again, you have a Brownian motion, but this time you take the path supremum until time t, and then you subtract the Brownian motion. So what this path transformation does is, this time, well, this is a little more sophisticated than the previous one, but in this path transformation, you have to look at the local maximum. And from this local maximum, there are some excursion below the maximum. What I mean with excursion below the maximum is the path starts at the maximum, then it goes below the maximum, and then it comes back to the maximum. And you have these excursions. Once again, you reflect them. to make them positive, and then you move this excursion to the 0. And well, this is how this path transformation works. What happened with this path transformation is that when a function is strictly increasing, it's just making equal to 0. But of course, a random motion doesn't have point of increase, so it is full of this excursion from the maximum. And okay, and what is behind this construction is, of course, this famous Skorokhod lemma, which tell us that if you have a real value function, then you can always add another function which starts at 0, is increasing or not decreasing, and that make these new functions not negative. But maybe the important property here is that the support of this measure is contained on the zeros of these new functions. So in some sense, this is like the most effective way to make this x function positive. So okay, and okay, this, well, I have already tell you how to construct this reflected Brownian motion, but to construct reflected diffusions is Skorokhod. Skorokhod idea was to introduce in his seminal paper this stochastic differential equation with reflections, which are essentially a stochastic differential equation, but you have to add these new terms that has the properties that it is essentially a local time. It is something not negative. It starts at 0. Well, maybe this condition is not needed in this description. It's not decreasing, and you need this property that the support of the measure is contained on the zeros of this function. And what is this talk about is that I want to tell you how to construct solution from this equation, from the stochastic flow associated to this and other equations. So let me recall you what a stochastic flow of diffeomorphism is. And the idea is that if this, okay, but before, of course, it is very well known. There are mild conditions to have existence and uniqueness for this equation, so this is very known. Oh, okay. But now we move to the classical differential equation. And if the coefficients are smooth enough, then there is a family of mappings that is called a stochastic flow of diffeomorphism that solves this differential equation, stochastic differential equation, and satisfies these properties that phi of t is equal to the identity. We also have this cocycle property. If we have like an independent increment property, and of course what it is interesting in here is that these mapping are diffeomorphism. And okay, this is like essentially the same results that we have for ordinary differential equation, but of course in this context it is very more sophisticated to have this kind of results. And okay, well, some people call this that it is essentially a Brownian motion in the group of diffeomorphism, but okay. And the most trivial example of this is this one. We only have this mapping is very elementary, but I think it's useful to have some insight of how these constructions arise. And okay. Okay, and then our Skorokhod lemma tell us that a reflected Brownian motion started at x is given in this way. But we can rewrite this in the following way in terms of the stochastic flow associated to the Brownian motion. It is very simple, but I think it is interesting to think it in this way. And it turns out that this construction is it is an interesting object. Actually, we have the following. Indeed, for any stochastic flow, even here for this, you don't need to have a stochastic flow of diffeomorphism. If you look at this process, it is actually a non-negative Markov process. And it is a non-negative Markov process that starts at 0 at x. Something happened here. Until it's touched the 0. Okay, I'm not going to try to write here because it looks strange. And okay, our main result is the following one. It is this: if you have a stochastic flow associated to this differential equation, and you know that sigma and b are smooth enough. I don't want to be very precise here. Of course, this produces a stochastic flow of diffeomorphism. Then you can define the following objects. Is this one? And of course, the intuition or the motivation for this object is just that we rewrite the Skorokhod map in terms of this stochastic flow. And you have these other terms. Okay, maybe this is a little more elaborated term. But the important thing here is that in this way, you have that these two processes solve an stochastic differential equation with reflection. That is that when these mapping are indeed a flow of a diffeomorphism that arises from this equation, indeed this is a solution to this classical Skorokhod differential equation with reflection. And I found this very nice, but
excuse me, this L indexed by x is the local time at the point x. This one.
well, this term is only this one.
So this is not a local time at the point x. This is just something else.
Okay, yes, that's right. It's not the local time. It's just
I see.
This object of here.
Okay.
And okay, and one would like to have to understand how this works. And we have like the following the description. Well, this behaves just like the ordinary flow until this flow starts at x, gets below 0. And then you have like a piecewise description. There are some points, G, from where you are going to start your flow. And these intervals are given by the excursion interval of some other stochastic process. It could be a little involved here, but the idea is the following. You have another process which is obtained by taking the Skorokhod solution on 0 if from 0 to infinite of this term. If you look at the excursion at 0 of this process, those excursions, the interval of that excursion are exactly the interval of the excursion of this process. And then you have to take the flow that start on those points. And this is, well, I put a picture here. Okay. And the idea is that there is a process that has some excursion intervals on the real line. If this is the interval, you take the flow from this to here. You take this flow on those intervals. And if there is no such interval, if there is not an excursion starting T, then this process is just 0. And oh, okay. Oh, something happened here. And there is something interesting that, okay, we have a piece of the stochastic flow. What happened before this G, this left for this left side interval, is that the stochastic flow starts at some point here, and then it touches 0, and then it goes up. It is something very similar with the third construction of reflected Brownian motion. Is something like here, this would be like a local minimum of some trajectory of the flow. And okay, and I want to show you another application of this. And okay, these authors.
Excuse me. Maybe before you go to applications, please, can you go back to the picture when you show the trajectory? Can you, because this is a flow, and it will be interesting to understand what is the behavior of the trajectory which starts from another point. For example, this will be 1, this will be 2. What happens with these 2 trajectories?
I have to move the. Okay. I think the idea is that there are like a countable number of trajectories here that you are going to take account of them. The another ones like do something. Yeah, I don't have. I could write. The another ones trajectories, they just go like something like this. They go like that, but we have to ignore them to construct like these excursions.
Usually, when we consider reflected stochastic flows for equation with reflector, it happens that it glue up with this one, and then they move together after this point. What do you think? Does it happen in your construction?
Let me see if I understand. Maybe you are I understand that you're referring for the flow, but of this process.
Yes, and I want to know what happened with for two different texts.
Okay, I'm not very sure. I think it happened what you say. The thing is that I haven't thinking in that way. You have okay. The idea is this also generate like a kind of flow. Of course,
yes, exactly. This is the question. Yeah.
Of course, this is not going to be a flow of diffeomorphism.
No. Okay, let's go further and discuss it later at the end of the talk.
Okay. 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 Well, these authors in several articles, they give an explicit formula for the Skorokhod problem with two reflecting barriers, and their formula is like the following. First, if you have a mapping like phi, then you have to apply the classical Skorokhod mapping to this. You apply the classical Skorokhod mapping, and then you have to apply this another mapping. Okay, and the first time that I read like this article, I was thinking that this mapping, it was going to be the reflection at A. In my naive way of thinking, I say, okay, you already have a trajectory reflected at 0, then you just have to reflect this trajectory at A to obtain an Skorokhod map on this window. But the thing is that that's not true. You need a more sophisticated map here. But with this stochastic flow approach, you can make this idea works in the following way. Here again, you start with a stochastic flow, and one more time, motivated by the previous construction, you can define like these subjects that we call a Skorokhod map of this flow, which is going to be like the flow reflected from 0 of this another stochastic flow. And once again, for every flow you can reflect it, but this time at A. We are reflecting here in this interval. Now we reflect on this another interval. And it happens something interesting that these Skorokhod maps in fact satisfy the cocycle property, which is this one up here. And then we can express this Brownian map with two reflecting barrier as the composition of this. Okay, here it works that idea. First, you have a mapping. You take its stochastic flow associated to that mapping. Then you consider that stochastic, that reflected flow, and then you reflect them from zero to the positive side, and then you reflect this flow from A to what is below A, and I think this is like a nice way to obtain this double Skorokhod map, or at least I think it's more intuitive or more natural. And that's what I want to essentially talk to you.
Okay, thank you very much. And I think we must have a lot of comments. Maybe Andrey Pilipenko is an expert in this reflecting mapping. So does anybody have comments or questions, please?
Well, I would like to make maybe really few comments for your theorem, because I studied a lot of properties of stochastic reflecting flows maybe 20 years ago, like coalescing, differentiability, and so on and so forth. And in your case, if you write your Skorokhod stochastic differential equations, then you can prove that this vector field is continuous in S, T, and X. And just use classical approach, moments estimates, like in book of Kunita.
Okay.
And on the other hand, before you hit zero, your process coincides with traditional non-reflected process. And another property is monotonicity in one-dimensional case. So if this point is greater than this, then solution to Skorokhod equation always greater than or equal to the lower one. Hence, assume that this function is at zero at certain point. Look at all of these processes. They are less than. What does it mean? This means that at this instant, they have the same value. But then you have uniqueness of the solution. So all these particles glue together and move like this. And now assume that you have a few reflections, and then you have the last visit. For example, this point is the last visit, and you want to understand what happens at the point T. And try to start from above and move this point down, down, and down, and you have monotonicity. And well, exactly your result is correct, absolutely correct. So you touch at certain level, and after this, all these coalesce together. all this all solutions started from below.
Huh?
Coalesce with this one, and if you know that there are no visits to zero, then this trajectory coincides with trajectory of non-perturbed stochastic flow. Maybe this idea will help you when you consider two reflecting barriers. And there is an interesting question: what happens in multidimensional case if you reflect from, for example, hyperplane? Do you have similar picture or not?
No, definitely. I don't. I have no idea how this could work in some more dimensions.
And I also think that you don't.
Andrey, sorry, but we have no time. And I think it will be very helpful for Ulises if you can send him several reference, yeah?
Okay.
It will be very good, but unfortunately we have no time to continue this discussion. Ulises, thank you again for your talk today, and we have to go to next speaker.
Of course, no, thank you to you for the comments and for the opportunity.
Okay. Okay, so our next speaker is Yurii Minialiyk from our institute, who will speak about geometric invariance of a random link. Okay, please, Yurii.
Hello, everyone. Let me share my screen. Before I start, I want to thank all the organizers for the opportunity to participate in such a mini conference. And it's a big pleasure to me to participate in this conference in the name of Anatoly Vladimirovich Skorokhod, who made a lot of contributions, and as we said, in theory of stochastic differential equations and overall in math. But the only thing that I want to mention that we not only need to remember what contributions made Anatoly Vladimirovich, but also remember what a person he was. Because as I know, he was very interesting and principled person, and I think his principles led him to his major achievements in science. So the subject of my today's talk is geometric invariance of a random link. And before I start, I want to say that I'm grateful to my supervisor, Andrey Anatolyevich, for his very fruitful ideas and comments that made this work possible. Okay, so let's start with short introduction. Nodes and links naturally arise in hydrodynamics and vortex dynamics. So as in this picture, like trajectories of particles of air or of liquid can move in these like node type trajectories. And when we consider such motions, for example, as a turbulence, small perturbation of the system, like it can be caused by error of calculations, like machine errors. The overall behavior of the system can change dramatically. Yes, but so our system will be like a chaotic. So one possible look at here is that our system almost become randomness, become random. So one can consider random nodes as these trajectories. And in our talk, firstly, we will give a construction of random node and random link. Then we will consider some geometric invariance of random links, just invariance of links. And then we will study the properties of this invariance of our random link. So let's start with some preliminary definitions. So we will say that node is a continuous embedding of a circle in space. For example, it can be such trefoil node. And when we project this node on a plane, we will get a diagram of a node. If we draw this, what arcs of a node are over and what arc is below. So we will have this diagram, and we will call such double points as crossings. In this case, we have 3 crossings. But sometimes can happen such a situation that we will have an infinite amount of crossings. For example, when we consider wild nodes, it can be like this. But the problem with them that they are all non-smooth. And in our consideration will only appear smooth nodes and smooth links. So we always have diagrams with finite amount of crossings. Link, we will say that is this just a union of non-intersecting nodes. It can be like 2 circles, like hop link, or it can be like this, like 8 figure with a circle. And this is like example, we will return to them further. And let us begin with the construction of random node. So I will recall the construction that made Andrey Anatolyevich, and I think he already made a talk about it on seminar devoted to Malyavian calculus and applications. But still, let me recall it. So let Xi will be from R2 to R3, be a centered Gaussian random field with independent identically distributed coordinates with the covariance like exponent of -1/2 of norm of a difference of minus v in square. We will denote this function as j from u minus v. So right now our function j from u is just exponent of -1/2 of norm of u in square. And it is important thing to mention that such function is positive definite. Because this is just a characteristic function of a standard multidimensional normal distribution, so it is positive definite. So we can construct such a field. Since the covariance is infinitely differentiable, then due to Gaussianity, Xi has an infinitely differentiable on R2 modification. So we can consider any derivatives over our field, and we not only can consider, but we also will use. So the construction is the following. Let us consider a unit circle in plane, and we will consider an image of this unit circle under the random field Xi. Then we will have some random curve, and this was theorem of Andrey Anatolyevich that he proved in 2023, that this random curve with probability 1 will be a smooth node, and the second one it attains any topological type with positive probability. So we can expect any type of node in this process. And we will slightly modify the proof that gave Andrey Anatolyevich to obtain a construction of a random link. So our construction is the following. Let us now consider 2 non-intersecting unit circles in plane and consider its image under the Gaussian random field Xi. And then our first result says that obtain pair of random curves will be a smooth random link. So now let me say what will be the idea of the proof. So firstly, these 2 components will be smooth random nodes due to theorem of Andrey Anatolyevich. And we only need to prove that gamma 1 and gamma 2 are non-intersecting. To do this, we consider the following lemma. So before that, we define functions that approximate a delta function at point 0. And our lemma says that if we will consider the following limit of integral of expectation of h epsilon from this difference gamma 1 t1 minus gamma 2 t2, this limit will exist and will equal to this integral. Let me recall that. Oh, sorry. So our function j from u is exponent this node. this integral converge because the denominator is equal to 0 if and only if this difference is equal to 0 vector. So our circles must intersect. But as they are non-intersecting, we can even say that they are located at some positive distance with respect to each other. So this denominator is bounded from below, and this integral converge. And the reason to this lemma is because if we consider just the density of this vector, it has density, like let it be T1, T2 from X, it has some density. Then this integral is just this density at point, the subintegral function is just a value of density at point 0. So we really just use this delta function property and then use Lebesgue dominated convergence theorem to get this lemma. And now we can use this lemma to prove our theorem. So suppose that A is a set of random events such that we have an intersection between components, and suppose that this probability is strictly greater than 0. Then we can take some random event from A, and by definition, we will have some intersection between components. And the idea here is that if we have an intersection between components, and we will draw an epsilon ball across this point of intersection, then our link will spend too much time close to this point of intersection. So precisely, we can write a definition of differentiability of our curves, and then it will exist some constant which will depend on omega and will be greater than 0 for almost all omega, such that the following inequality holds. And now, if we will take expectation and take a limit epsilon tends to 0, we will have infinity. So this will contradict our lemma 1 about such that this limit must exist. So we will have a contradiction, and hence we get a construction of random link. So now let's move to main definitions of invariants that we will discuss. So first we will define linking number. To do that, let us consider a diagram of a link, and we will define an orientation of the components. Just simply, firstly, we take an orientation which is defined by parametrization. So we have orientation of each component in space, and when we project, we just preserve an orientation. So we will have such crossings of two types, and we will say that the first type of crossings have sign +1, and the second one have sign -1. And we will give a such definition then that the linking number of link which consists of two components is just the half sum of signs of crossings. Let's look for some example, like it can be Hopf link. Let me use orientation in this way. So we have here the following. So we have here sign +1 of this crossing, and here we also have a sign +1. Yes. So the linking number will be equal to 1 in this case. Now let's choose another orientation. For example, I will change the orientation of a blue circle. And I will choose an opposite orientation. Okay. So now here we will have a -1, and here we also have a -1. So linking number will be equal to -1 in this case. So what can we say? If we change an orientation of one of the components, linking number change its sign to the opposite. And And in white-head link, let me choose the orientation in the following way, like this way. So we will have here -1, -1, +1, +1. So in this case, linking number is equal to 0. However, these two components obviously link. So it is important to understand that a linking number is not a complete invariant. So if linking number is equal to 0, it doesn't mean that we have two unlinked nodes. So this situation can happen. And with this definition, let me go back. With this definition, a lot of questions might be asked. For example, why does this definition doesn't depend on the choice of particular diagram, or how we can find this linking number if we have a parameterization of curves, and maybe why does linking number is always an integer? And all these questions were answered by Gauss and his famous Gauss linking integral. So Gauss linking integral is the following integral. So it says that the linking number is equal to this double integral in the case when gamma 1 and gamma 2 are parameterized by intervals 0 to pi. We have this determinant of three vectors in the numerator, and in the denominator we have the norm of the difference in the power 3. And the idea of this formula is the following. Let us define psi from a torus to a unit sphere, which will be defined by this relation. And psi is a Gauss map. So idea here is the following. It occurs that the linking number is exactly a degree of a Gauss map. So in other words, linking number is the signed number of times that the image of a torus covers a unit sphere. And now we can see that at the right-hand side, subintegral function is exactly a Jacobian of a Gauss map. So this integral really counts this number of times that we cover a unit sphere, because also we divide by 4 pi, and 4 pi is obviously an area of a unit sphere. So this is such integrals that we will use. And next invariant is the a little bit trickier, is the average crossing number. So let P be on unit sphere, and let n gamma p be the number of crossings between gamma 1 and gamma 2 in a diagram of a link when link gamma is orthogonally projected on some plane which is orthogonal to p. So we project in direction p. And all such directions for which n is not defined or like infinite are exactly the critical values of a Gauss map. We will not prove it, but just say it because it's not the main point of our talk today. And by Sard's theorem, the set of critical values have zero measure. This gives us the opportunity, not us, but Friedman and Zhengchu He, if I pronounce this correctly, to define an average crossing number. It will be a double integral, so integral over the sphere of this number of crossings. And the most interesting part about this is that this average crossing number have representation that is very similar to Gauss linking integral. So it is just an absolute value of a subintegral function that is in Gauss linking integral. And the reason for that is just because average crossing number, it will be just the number of times that image of Gauss map, image of torus under Gauss map covers unit sphere. So such interesting invariant, and we proved an interesting lemma about this invariant. So we proved that if average crossing number of a link is equal to 0, then gamma 1 and gamma 2 are non-intersecting trivial nodes on some plane in space. So average crossing number can be equal to 0 if we have like link in a plane. And the reason for that, let me come back. We have this integral representation, and subintegral function is non-negative. So if it is equal to 0, and we have gamma 1, gamma 2 are smooth. So we have such that for any t and s in 0 to pi, we have a following determinant that equal to 0. So the proof of this lemma is just abusing of this condition. And idea here is the following, that this condition gives a link a smaller amount of directions to change. So our link can't change in 3 directions. So it must live in a plane. So this is what an idea here. And the last invariant that we define today is the Mobius energy of a link. So let firstly d capital of gamma 1 t gamma 1 s be the length of the shortest arc on gamma 1 between gamma 1 t and gamma 1 s. And then one can define an Mobius energy of a link. So firstly, one can define a Mobius energy of a knot gamma 1 by this double integral. So one can see that this is some kind of a potential energy, and we can define a cross-like energy between two components, and then epsilon from gamma is a total energy of a link. The reason for that to be called a Mobius energy is because such energy is invariant under inversions with respect to spheres and affine similarities. So it is invariant under Mobius transformations. And also there is interesting facts. For example, energy of a straight line is just 0, energy of a circle is 4, and actually the minimum of energy among all knots is equal to 4 and achieves only for a circle. So these authors, they prove this statement in a paper which they defined as this Mobius energy, and it will be in the references later. So now we can go to the main statements. So we have gamma is a link of two components, gamma 1 and gamma 2, and we have following statements about this invariance of defined random link. So first one is very simple. Linking number has a symmetric distribution. And the reason for that is that we can consider a reflection of these two nodes with respect to point 0. And because our random field Xi is a centered Gaussian isotropic random field, when we reflect, we will have a new random link that will have the same distribution as the starting one. But at the same time, by Gauss linking integral, we have the following relationship. So when we reflect, so we have this minus gamma 1 minus gamma 2. In linking number, we have this determinant of 3 vectors. Yes, so we will have 3 minuses, and the minus will come up before the linking number. So we have this simple property of linking number, and we can prove a much more interesting property of average crossing number. So probability that average crossing number of a random link is equal to 0, this probability is just 0. So to prove this theorem, let us firstly use the lemma about average crossing number. It says that if average crossing number is 0, then our link lies in some plane. So we can consider a probability that each of components lie in some plane. And now we can define a function f, which will be just a determinant of 3 and 3 matrix. And now we can consider 4 points on an initial circle that we map in a random node. And we can define such a determinant of these points on the node. So if our node lies in plane, then at least 4 points lies in one plane. Then this determinant must equal to 0. So we have a following probability that determinant x is equal to 0. And we will prove that this probability is just 0. To do that, let us firstly recall that the covariation function j of random field Xi is positive definite, then random vector, such a random vector has density. So now we map a vector with density using function f, which is our determinant, and then it occurs that the determinant will also have density. And the reason for that is that firstly, f is infinitely differentiable, so it's locally Lipschitz. And by cofactor formula, we can write it in the following way. So we can find a gradient. It will be a square root of sum of squares of minors. And then the gradient is non-negative, so it's positive almost surely. So now we can use a co-area formula. So we can write a probability that determinant is AB as an integral over pre-image of interval AB over function f. And then use square formula to represent this as an integral over level sets. And in this formula, H8 is 8-dimensional Hausdorff measure. So if we differentiate, we will get that our determinant D has density, which is defined by this formula. So let me go back. So this probability then equal to 0. So this finishes the proof. Let's move further. This statement gives us two useful corollaries. First one, with probability 1, there exists a plane L such that orthogonal projection of a link on it has at least one crossing. And the second one, with probability 1, there exists plane L such that orthogonal projection of gamma 1 on it has at least one self-crossing. So that means that anytime we can expect to have at least one crossing in a diagram of random link or random knot. The next theorems are devoted to existence of moments. So first one is that we have moments of average cross number of orders from 0 to 3/2. We don't have enough time for this. So to main point, we need a convergence of this integral. And this expectation is finite only for p from 0 to 3/2 and have the following value. If we integrate this, this integral will converge because our sigma is bounded from below because our initial circles are not intersecting. This is the idea here. And we can use this statement as a corollary that we have moments from order 0 to 3/2 of linking number. This is because linking number is, as you remember, Gauss linking integral and then integral that defines an average crossing number. So we have absolute value of linking integral is less than or equal than crossing number. So we have such corollary. And the last one is devoted to Mobius energy. So a total energy of a random link have moments from order from 0 to 1/4, and the moment of 1/4 is infinite. So here is the main point that we get the same integrals as in previous theorem, plus we have the integral, this integral when we have a gamma 1 equal to gamma 2. So to estimate this integral, we use similar approach. And we just get the convergence when moment p is less than 1/4. So that's all that we have for today. And we have a corollary for average cross number just of not over itself. So that's all that we have for today. This is references. And thank you for your attention.
Okay, thank you very much. We have just very short time for just one comment or question, please. Okay, I just want to say that we hope to continue this investigation and to discuss the evolution of such topological properties of the random knot in stochastic flow which is generated by the smooth stochastic differential equation with interaction. Okay, thank you again, and we have to go to the next talk. Now, next speaker is Yifan from Jilin University with the talk Complexity of Flows with Interaction and Stochastic Analysis. Please, Yifan.
Okay, let me share my screen. Okay, hope everyone can see my screen now. Good evening, everyone. I'm a bachelor student at Jilin University, supervised by Professor Andrey Dorogovtsev. Today, I'm honored to present our work on the complexity of flows with interactions and the stochastic analysis. This research bridges stochastic processes, measure value dynamics, and fluid mechanics, with a focus on systems of interacting particles and vortices in random media. Let's dive in. Let's begin with the foundational concepts. Our starting point is the equation with interaction. In this presentation, we will consider the equation with interaction which was introduced as a mathematical model for evolution of the systems of large number of interacting particles in random media. The definition is as follows. Let mu0 be a probability measure on the space Rd. The equation with interaction has this form, like this. Just note that the measure mu_t here is a push forward of the initial measure mu0. Then this equation was firstly considered by Professor Andrey, this reference. In these systems, the measures are presented. So we need to extend the Lipschitz condition for the function which depends on the measure valued argument. Due to this, let us consider the space of measures and the distance in this space. Suppose X rho is a complete metric space. The space M is a space of all probability measures on the Borel sigma field. For two measures nu and mu, we can define the Wasserstein distance of order 0 between these two measures like this value, where C mu nu is the set of all probability measures on the set of all probability measures on the Borel sigma algebra of the direct product, which have mu and nu as its marginal projections. Similarly, we can define the Wasserstein distance of order n. First, also denote the space of all probability measures as a finite n moment. Then we have the Wasserstein distance of order n between two measures as this value. We have two remarks about the properties of the Wasserstein distance, Wasserstein space and Wasserstein distance. Firstly, convergence in gamma 0 is equivalent to the weak convergence. And secondly, this space Mn, gamma n, is a complete separable metric space for all n if X is separable. But these two remarks are not that important in today's presentation. Okay. Next, let us consider Helmholtz system for infinitesimal vortices. The system of vortices can be seen as a partial case of the equation with interaction. The description of the dynamics of vortices in two-dimensional space goes back to Helmholtz, who established the vortices as the particles of fluid mechanics. The definition for the Helmholtz system has this form. This notation Pj denotes the vorticity of the J's vortex. In general, vorticity can be positive or negative. due to the direction of rotation. The interaction between vortices depends on both their positions and their vorticities. In this particular setting, for simplicity, we assume that all vorticities Pj are positive. This assumption helps us focus on the core features of the collective dynamics, especially the rotational interactions. Okay. While the equations we study are idealized and simplified, they are indeed inspired by real phenomena observed in nature. To illustrate this connection, here's an example of vortices as they appear in the natural world. Since we have the Diffusions condition on the coefficients of the equation with interaction, then we hope to have a unique solution. Now we consider the vortex equation as a partial case of the equation with interaction. We prove it can have solutions not only for discrete measure, but also for continuous measure, which concentrated on some smooth curves. Now we will introduce two theorems about the solution. The first one is the discrete case. Consider the Heorhii system for infinitesimal vortices for Cauchy problem like this. Then the solution to the Cauchy problem exists uniquely. The proof of this theorem is not our main point today. Let us show the continuous case and also its proof. For continuous case, let the initial measure mu0 be a visitation measure of smooth curve, defined as follows. Then, for the Cauchy problem for differential equation with interaction, when initial mass distribution is a visitation measure of a smooth curve, then consider this equation we have. The existence of the solution can be proved, which is also unique. Okay, so for the idea of proof, the main idea is construct a sequence of iterated equations, then obtain corresponding solutions and measures. Then we can use estimation to prove convergence. This procedure can be proceeded as follows. First, fix t as a positive number and consider the equation on the interval 0 and t. Our first step is to consider such x1, and the measure here is mu s0, and is always be initial measure mu0. The existence of the unique x1 follows from the Lipschitz property of the coefficient, this coefficient with respect to x1. More precisely, let us denote h1 as the coefficient. Then we can check that the summation of partial derivative is bounded. Thus, we can apply the finite increment theorem to obtain the Lipschitz property. Moreover, note that in this estimation, we don't need some special properties of our curve G. Therefore, such procedure can be repeated during the iteration. Then, for the next step of the iteration, we can denote mu1 as a push forward of mu0. Now we can define x2 as a solution to this equation. We substitute the measure mu0 to mu1. Then the existence of unique x2 also follows from the Lipschitz property, which can be checked by the same way. So, as a result of such a procedure, we obtain the solution sequence xn and also the corresponding probability measure sequence mu_n. Next, we can denote the coefficient f as this. Then we want to show the Lipschitz property of all coefficients. Firstly, we apply the Lipschitz property with respect to x. Then we want to estimate this term. Okay, for arbitrary kappa belong to this set, we can continue our estimation. Then finally, we can say the difference between measure in the Watersink distance sense can use to control the difference of our iterated flow. Moreover, we have the following estimation. This one and the following iteration. Thus, now the situation is more like the Yurii way in ordinary differential equation. Then when we obtain the existence and the uniqueness of the solution. Now let us show two invariants in our consideration. The first one is center. The second one is the moment of initial. It's not hard to see that in our case, the solution of the previous question problem also has the following two invariants relatively to the classical Humboldt system. Now let us start the discussion for next chapter. We will study the asymptotic behavior of the equation with interaction to understand it much more properly. To do this, we need to find a proper description for the measures since the space of measures is non-linear. From this point of view, we proposed a lifting to Gaussian space, and we proposed to substitute the measures by the integral. It occurred that the measure is uniquely defined by such integrals. We will start from the definition of the white noise in the separable Hilbert space H. A Gaussian white noise could see in H satisfying the following properties. The first one, the combination of elements in Hilbert space and Casimir is a Gaussian family, linear with respect to G. And secondly, it has zero expectation, and the covariance can be expressed by the kernel function, which we usually choose in this way, by this gamma. And we also assume that in our consideration, H is a twice continuous differentiable function. In some literature, such construction is also called the isonormal Gaussian process. Also note that the combination here of the elements in Hilbert space and Casimir is somehow artificial, which we will see in this example. The combination in this separable real Hilbert space H is defined as follows, defined by the orthonormal basis. Then we can introduce the form of the equation in the interaction with stochastic term. Usually it was used to describe the flow with interaction in random media. The only difference is here we add a stochastic term, and we use capital W is the Brownian sheet in RD. Our aim is to construct the stochastic process and investigate its properties. We construct eta t as this following way, where Casimir is independent of the Brownian sheet capital W. Now, let us show a very important theorem that the measure here is uniquely defined by such integrals. Thus, we can consider the integral instead of the measure. The idea of proof is, from the condition here, we can get the integral is equal. Then, since the Fourier transform of the kernel function gamma is not equal for arbitrary lambda, we can denote mu as the difference between mu1 and mu2. We have 0 can be rewrite in this way. Let me get this. that the product of the Fourier transform of gamma and mu is equal to 0, which implies the Fourier transform of mu is equal to 0. Then, finally, we get mu1 equal to mu2. This proof is essentially based on the construction of the kernel function. Okay, then we can check the condition of Kolmogor's continuous modification theorem to prove the process eta t, which we constructed, as continuous modification. More precisely, the coefficient, the parameter gamma belong to 0, 1 over 2. We have this gamma hold a continuous modification for our eta. The idea of proof is just can be just checked by estimation and calculation, which is not hard, so we omit the proof here. For the last part, we will discuss the limiting behavior of eta t. We will show our motivation by an example to describe the so-called Kuromoto model. The form of the Kuromoto model has the following governing equations, like this. This model can exhibit synchronization for a finite number of oscillators. More precisely, it was proved that finitely many Kuromoto oscillators would reach a stationary state as t tends to infinity. Thus, we can apply the Kuromoto model to construct an example of stationary behavior. Suppose our measure mu t is defined by this way. Then, in our construction, eta t is defined as this. We can consider a sequence of eta n defined by eta nt equal to eta t plus n. Then, by the property of the Kuromoto model, there exists a limit of covariance. We denoted it by the covariance infinity, and this function only depends on the difference between our initial time t and s, which implies stationary. Then, in our consideration, for the formal description of such behavior, we will use some definition and theorem in this book. The first definition is the so-called shift compactness. A set of random measure mu alpha is called shift compact if for every alpha there is a random vector u alpha such that the shift of mu alpha with respect to u alpha is weakly compact in this space Mn. The idea is, although the original measures mu alpha might be not compact, but we hope to find a vector such that after this shift with respect to this vector, the measures are compact. We also need a theorem for the sufficient condition for shift compactness. Assume that in this function, which mu0 satisfying the such initial condition belong to the m to m plus 2, phi satisfying the condition. This condition guarantees the monotonicity, which helps the proof of the shift compactness. The coefficient b lies above results. We have the following result of the asymptotic behavior of the equation with interaction in our construction. So our theorem is under the condition in theorem for sufficient condition for shift components, just this theorem, we assume that the same construction in the example of Kuromoto model, we assume eta k equal to eta dot plus k. Then we have these properties. More precisely, I mean that in our construction, we can also find such function covariance infinitely, which also depends only depends on the initial time t and s, the difference between the initial time t and s. Okay, then for the idea of proof, denote the mt as the center. We can find that mu t after the shift of mt satisfying the Cauchy criteria, and actually this is the we call the definition of the shift companions. The mt plays a role in this random vector u alpha. Okay, then we denoted the limit of this measure by nu infinity. Then, by the dominated convergence theorem, we can say the covariance converges to this function. From this point of view, the covariance infinitely exactly has this explicit expression. And the convergence is guaranteed by such consideration. We take this estimation and the dominated convergence theorem to obtain the these results. Okay, this is all of my presentation today. Thank you for your attention.
Thank you very much for your talk, and we have 5 minutes for questions and comments. If somebody have questions or comments, please.
I have a question concerning the example of the Kuramoto model. So, did I understand correctly that you have proven that the synchronization even happens if you have more general measures than just Dirac measures?
Actually not proved by me, but proved in this reference. Under some more precise consideration, the Kuromoto model can behave synchronization. We just apply this property to construct our example. We actually in my consideration in my research, we do not make some generalization for such Kuromoto model. We just take it as an example.
Okay, thank you.
No problem.
Okay, other questions, please? Okay, if there are no any other questions, then we have 5 minutes break up to the next talk. Okay, let us continue our work. And the next speaker is Ruibo from University of Warwick with the talk on stochastic Casimir effect. Please, Ruibo.
Okay. I hope everybody can see my screen. Thank you very much for the introductions. And my name is Ruibo, and I'm a PhD student at the University of Warwick. And the talk for me is the stochastic Casimir effect. This is a joint work with my supervisor, Rosa Tribe and Oleg Zaboronski. And so first of all, what is Casimir effect? So imagine that you have two walls that place in a vacuum. And these walls may have some interactions with the particles. For example, it can reflect particles or it can absorb particles. So when the distance of this wall is small, there is an attractive force that pushes these two walls together, which is known as the Casimir effect. So if you think about this in the classical physics world, this can never happen because vacuum basically means nothing, no particles, not even light. So you cannot create force out of nothing in the classical physics world. However, it is possible if you treat the vacuum to be the quantum field. So in quantum field, pair of particles are constantly show up. So pair of particles, I mean particles and its antiparticles. And when they show up, they behave like particles. And when they meet, they annihilate, they disappear. So on the right-hand side, I draw pictures of this one-dimensional quantum field. So if you think about this part here, this is a pair of particles that show up. Sorry, the vertical line is the time and the horizontal line is the space. So this part, you can think about this as a pair of particles. It show up, and then when they meet, they disappear. And there are a lot of black dots here in these pictures. So if you kind of zoom in, then it is the same pair of particles show up, and when they meet, they disappear. And occasionally, some of particles get good luck, and they might, for example, this pass, they might live a longer life, like that. Okay. Now, imagine that if we put two walls in between with distance L, and especially when the wall, the distance of the wall is small, then the particle density inside the wall may not be the same as particle density outside the wall. Okay? So if I got more particle concentrated outside than inside, then this kind of attractive force can be created. And this is known as the Casimir effect, and it is actually shown that the vacuum is in fact a quantum field. Okay. And our goal is to construct a stochastic model for the Casimir effect in the one-dimensional cases. Right? So how are we going to do this? The idea is to, first of all, I drew a pair of particles, a soup of identical particles, which are created in pairs and with some constant rate. And each of these particles behave, and when they're not meeting, they behave like Brownian motions. And when they meet, they immediately disappear, like annihilated. Okay. And then we put two walls with distance L, and we consider both cases. The one is for the absorption, when the wall absorbs particles, and the other is the reflected case, when the walls reflect particles. And we only consider the steady state case. So if you think about this, these three descriptions, it is in fact a Markov process. So it should depend on time t. But what we consider is mainly the steady state. So we let t goes to infinity to hope that this system reaches out. Okay. And as I suggested previously,
excuse me, but before you say that you consider stationary case, it exists, yeah?
Yes, exactly. I will put this in the last previous. Okay, thank you. So now, so far, if you believe that the steady state exists, Then the main idea is to compute the particle density, rho of x. So this is can be defined by there is particles around x. Okay. So if you integrate these particle density functions, let's say between A and B, then there is expected number of particles between A and B. Okay. So since we consider steady states, this part is independent of time. Right. So firstly, we consider the Casimir force at the reflective wall. And the main motivation here is that if you consider this is the wall and it reflects particles, so each of the particles transform the same quantum momentum to the wall. Okay. So what we're going to do is I consider the particle. If you think about this is the particle system between 0 and L, and the particle reflected between 0 and L, then this is a particle system. And then I can compute the particle density inside this wall. And then I evaluate at 0. I will call this particle density rho 0 minus. And if you consider particle moving outside the wall, then these particles, they reflect at 0, only at one wall. So it had different particle density. And I can also compute the functions and evaluate at 0. I will call this rho 0 plus. So I will use the difference of this two particle density at 0 to represent the Casimir force for the reflected case. Okay. All right. So now the result is here. For the this annihilated Brownian motion with pairwise immigrations, this beta is the immigration rate. So this is just the system I described previously. So particles is reflected at 0 and L. Then the expected Casimir effect can be written in this formula. And it has some asymptotic behavior. So the asymptotic behavior, it decays with respect to L exponentially fast. If you think about this, it decays quite fast, which is the same as the realistic, because in the realistic, only when the distance of the wall is small can we detect such force. If you increase this distance a little bit longer, then you cannot see this force. So that means it decays with respect to L very fast. Okay. All right. So another result is we consider the wall to be the absorbed wall. Okay. And then the motivation is here. The force is proportional to the flux of particle into the wall. So the reason you can think about this, imagine that there is the invisible wall. So the flux is that the total number of particles that come from from the right-hand side pass it, minus the total number of particles come from the left-hand side that pass it. So the difference of this two part is the total number of particles that are absorbed it. So that's why the force is proportional to the flux. And it turns out that the flux is proportional to the derivative of particle density. So that's why we use the derivative of particle density to represent the Casimir force in the absorbed case. Okay. So again, this part is the particle density inside the wall, and this part is the particle density outside the wall. Well, it should be evaluated at 0 as previously, but the trouble is if you compute this number and evaluate at 0, it is an infinite number. So you cannot take the infinite number minus the infinite number. So what I do is I consider this flux a little bit away from these two walls, and then take the difference and then to take the limit. Okay, because it turned out that the speed that these two numbers converge to infinity is the same. So the difference reaches some constant number, which is some finite number. Okay, and here's the result again for the for our model, the annihilated Brownian motion with the pairwise immigration. And if we put two absorbed wall between 0 and L, then the force is written in this long expressions that is written by theta functions. So this theta is here, it means theta functions. Okay, it's just some special functions. And we also did the asymptotic analysis for that. is the it decay again even faster. It can exponentially divide by square root of L. So it is faster than the reflected case. Okay. Here I plot these two forces. So the left-hand side is reflected case, the right-hand side is the absorbed case. So you can see from this this pictures that the absorbed case it decays faster. All right. So how are we going to do this? The idea is very easy. We just firstly consider it in the discrete lattice, and then take the scalar limit and hope that it reach some process on the continuous space R. Believe me that such things exist, then that's what we're going to do. So firstly, we consider the random walk on the scaled lattice, the analytic random walk on scaled lattice. So the first line is the right jump rate for the Markov process. So this particles is trying to jump to the right-hand side with the rate 1. Okay. So then I got no particles, so 0 on the left-hand side. And then when this particle jumps to the right, I get the sum of these two particles. Okay. But this is not the sum, but addition of the mode 2, because we want to create a analytic particles. So 1 particles plus 1 particles should be 0. So it should be 1 plus 1 equal to 0, which is exactly the mode 2 computation. Okay. So similarly here on the left jump. So there is a particles jump to this left. Okay. And when you jump to the left here again, this is a mode 2 computation, and then the right part will leave empty. Okay. And we still keep throwing pair of particles like what we do in the Casimir effect. We throw a pair of particles with a scaled rate beta next to each other. So this is eta x, this is eta x plus epsilon, and each of this position is adding 1 particles. Here. And this is the immigration rate. So this is the analytic random walk with the immigration. Okay. Then we can define our process. Well, not only scaled for the space, for the lattice, but also scaled by time. It's like what we do in the Brownian motion case. So this means, this just means that the right-hand side just means that the total number of particles in the set. So give me a set, and then I restrict it on the strict lattice and compute the total number of particles in that. I will call this process the xt epsilon. And this xt is what we're going to study. Okay. Now, first we just need to compute the particle density. How are we going to do this? The proof strategy is that we consider this kind of duality functions, or the this called the parity of the particle. So we call this VT. This V functions is well here that means the total number of particles between x and y. Why it's called parity of particles is if you think there is an even number of particles between x and y, and then this should give you 1. If there is an odd number of particles, this should give you -1. So that's why it's called the parity of particles. So why are we going to study that? Because if you increase x a little bit by epsilon, and then minus that divided by epsilon, what you get is the probability that there is a particle at x. It's just a computation. And now you let epsilon goes to 0, this part will converge to the point density, to the particle density at time t. Okay. And if you let epsilon goes to 0, the left-hand side is going to be the derivative of the duality functions, of the parity of the functions. So now we just need to compute this duality functions. And the way that we compute it is just a generator calculus, because the generator calculus is nothing else but taking the time derivative. So just apply the generator on the both sides and derive some kind of PDEs and solve it. Okay, that's the idea. So here is the generator calculus. Apply the generator, as I said, this is just the time derivative. And the right-hand side would be Laplacian minus 4 beta. So the Laplacian comes from the random walk part, because random walk always give you a Laplacian. And this 4 beta comes from the integration part, because we threw a pair of particles. Okay. A boundary condition at x is, if you take x equal to x, both of this part equal to x, so there is no particles between x and x. Okay. So the number of particles between x and x should always be even. So it will give you 1. And in the beginning, we start with no particles. I start with no particles and then through a pair of particles. So in the beginning, I have no particles. So that means the parity of particles should always be even. So that means it is always equal to 1. Okay. And remember, we still have 2 boundaries that reflect or absorb particles. So we put 2 boundaries. We still need to check the boundary condition 0 and L. And checking that is, again, generator calculus. And if you apply this generator here, what you see is that for the reflecting wall, you have a Dirichlet boundary condition. And for the absorbing wall, you have a Neumann boundary condition. A small remark here is that if you consider just the reflecting Barney motions, it should give you Neumann boundary condition. And absorbing Barney motion should give you Dirichlet boundary conditions. But here we consider the duality functions. So this duality function kind of flip this property. Okay, now as I suggest, I consider the scalar limit. So I will let epsilon goes to 0. So here, everything can be written in the continuous space. So the discrete Laplacian will become the true Laplacian. Okay. Now we also take t goes to infinity to reach some steady state. So we also let t goes to infinity. So on the left-hand side, if I take t goes to infinity, I don't have this time derivative. And I still have these boundary conditions, but I cannot forget about the initial conditions. And again, we have some boundary condition at 0 and L. So either Dirichlet or Neumann boundary condition. Okay, so now the rest of the work is just write down this PDE and solve it. After that, just take the derivative of these duality functions. Then we will get the particle densities. And then we can use this particle density to compute the Casimir force. Well, that's the main idea. Okay. So now if we solve it and then compute the particle densities, and then what do we get the formula for the reflecting wall is this formula. Okay. And the asymptotic analysis for that is easy. You just write down everything, and then you will see that this decay exponentially fast. Slightly difficult is for the absorbing cases. If we write down everything, and then the absorbing wall, the force can be written in the, well, this, I only write down the leading term here. It is written by theta functions. Okay. We need to do the asymptotic analysis for that. Before that, a small remark is why the theta functions show up. So if you think about the heat equations with Neumann boundary condition, then the green function for that is exactly written by theta function. So it is reasonable for us to have a theta function, also have a theta function here, because our function is just a heat equation with a constant potential. Even though I didn't solve it by construction of green function, but this theta function still show up. Another reason why I like theta function is because of this Jacobi identity. So the Jacobi identity gives us, I can rewrite this theta functions by another theta function times this part. So why this is useful is because the new theta function here, if you take u goes to 0, then this part will convert to a constant number. So when you do asymptotic analysis, I can kind of forget about this constant part. So only consider this part. And this part is quite easy. So as I suggest, I just plug in this part here. And then this will be a write it in this way, and forget about the constant term. And the asymptotic analysis for that is just a Laplacian method. You compute the second derivative of these functions and then compute its critical point and then evaluate everything. Okay. Okay, that's how we derive this Casimir force. So, so the last part, I will talk about the existence of our systems. So why the scaling limit exists and why the steady state exists. It turns out that the existence of the scaling limit and the steady state, they all comes from the fact that we are considered the Pfaffian point process. So what is a Pfaffian point process? Let's define Pfaffian point process on the lattice. It is called Pfaffian point process if we can find a matrix such that any n-point density, so the probability that I have a particle at x1, x2 until xn, if this probability can be written as a Pfaffian of a matrix. So what is a Pfaffian of a matrix? It's just take the determinant and then take a square root. If we can write this particle density or this probability by a Pfaffian of the matrix, then we call this a Pfaffian point process. So the matrix kernel here, each of this matrix kernel is a 2x2 matrix. You can write in this way, and they must be antisymmetric. The reason that it is antisymmetric is because I want this Pfaffian to make sense. If you take a general matrix, then this determinant might be negative, so you cannot take square. Okay, so I will recall a theorem proved by another student of my supervisor and my supervisors. Previously, the annihilated random walk model with the immigration model, at a fixed time, it is a Pfaffian point process on the discrete lattice. Okay, the kernel, the Pfaffian kernel, can be written by the duality functions or by the parity of particles. So this D plus is just a discrete differential operator. And D2 means that act on the second variable, and D1 means act on the first variable. Okay. So that's why we focus on the duality functions, because the duality function not only give us the one-point density, but in fact, it gives us the any point density. So in principle, if I know the any point density, I should be able to know everything about this particle system. So that's why this duality function, computing this duality function is quite important for us. Okay. So if we know that the discrete case, it is a Pfaffian, again, we can apply a first theorem proved by my supervisors. So if the kernel converges, and we know that the derivative is bounded, then the result is that the Pfaffian point process will converge to a Pfaffian point process. Okay. And the limit is again exists, not only exists, but also Pfaffian. So here, what I mean on the continuous space, so what I mean by it is Pfaffian is that again the n-point density. So there is a particle around d1, dx1, dx2 until xn can be written by a Pfaffian of a matrix, and the kernel can be just written by the continuous version. We just change the discrete differential operator by the continuous differential operator. Yeah. Okay. So that's why the continuous limit exists, because we just check this, the boundedness of the derivative. Then a sequence of Pfaffian point process will converge, and the limit is still a Pfaffian point process. And that's also the same reason for the steady state converge. The steady state exists because each of this Vt, each of this continual time system is a Pfaffian point process by this theorem. So if we let t goes to infinity, a sequence of Pfaffian point process should again converge to a limit, and the limit is again Pfaffian point process. And the kernel is just written by you change this t, let this each of this t goes to infinity. Well, I think that's all for my talks. Thank you for your attention. Thank you very much.
Thank you very much for interesting talk, and maybe we have a few times for few questions, please.
I have a question. So can you hear me well?
Yes, yes.
Yeah, so this problem reminded me of the so-called Hawking radiation. So the setting is that near the black hole, near the surface of a black hole, there are always emerging pairs of particles, antiparticles.
Yes.
And one of them gets into the black hole and the other gets radiated to the space. And this is called Hawking radiation. And it seemed to me that it's very close to your problem. So maybe there is some kind of interesting connection and possibility of physical results there. What do you think?
Yes, I think, first of all, I never heard of that that property. But yes, I think that looks similar to this problem. If you think about the absorb wall to be the black hole, it always absorbs particles. But I don't know, if you create a pair of particles and antiparticles, is that always true that one of this is going to be absorbed, the other way escape? Because in our cases, most of the particles is going to come back and annihilate with each other. But I don't know, is that the same in that case? Or
I also don't know much, but I think the results are very interesting from the physical point of view. So it looks like the black hole should become smaller and smaller because of this radiation at a very long period of time. So this is something interesting to look up.
Yeah. Thank you for your. So could you please remind me what that property, the name of that phenomenon?
It's called the Hawking radiation. So the Stephen Hawking, you know.
Oh, okay. I see. Oh, all right. Thank you.
Okay, some other questions, please.
A question: what's the typical behavior of particles in your Python model?
Yeah.
Is there some repulsion, or they tend to cluster?
Sorry, what do you mean?
Well, if they're forced to keep away from one another, so what happens with this density if the particles are very close to one another?
Yes. Yes.
So for instance, if you have a Poisson process, it doesn't matter. And if you have this sort of deterministic process, then there could be some force moving them apart when they come too close to one another. So it should lie in the nature of this K, of this kernel.
Yeah. Yes. Yes, I think because the particles create in pairs, and in the beginning they cannot annihilate. So yes, I think you're right. There is some force that push in the beginning that push these two particles away, but I don't know how it's gonna reflect it in my kernel.
Happen that you have no right description what happened with really pair of the particles. They have to be independent Brownian motion, but it can give you like length in a Ratia flow. Maybe you know this effect. So you have like hole in Aratia net. Yes. So it looks like this. because you already have stationary behavior.
Yeah.
Also, let me ask you about the some other characteristics, physical characteristics and force in your effect. Because as we have stationary behavior and we understand that energy must be the same, so maybe you can think about some other physical characteristics of your system than just force at the end of the interval.
Okay.
Yeah, there is such a notion as a fluctuation of energy. Total energy can be constant, must be constant, but fluctuations of energy can happen. Yeah. So it can be interesting to think about such physical characteristics.
Okay.
Okay, thank you again. Now we have to switch to the next talk. Thank you very much. And the next speaker is Heorhii Zhylinskyi from Ukrainian Physics and Mathematics Lyceum with the talk Random Links and Random Walks on Finite Groups. Please, Georgi.
Yeah, so hello everyone. I'm very happy to be here at this conference today. And I would also like to thank all the organizers for making this conference possible and my supervisor, Andrey Anatolyevich, because without his contributions, this presentation wouldn't be possible. Okay, so today I'll be talking about random links and random walks on finite groups, but before I talk about that, let's quickly go through some basic knot theory. So knot is just an embedding of a circle in R3, and a link is basically just a disjoint union of knots. So here we see two examples, a trefoil knot and the half length. Okay, so there is another related concept to that, a braid. So it's a bit of different nature. So the way it is constructed is that you have two parallel lines lying into parallel planes. And we have endpoints lying on each one of them. And we join these points by arcs. So as shown in the picture. And they must satisfy some properties. So for instance, here, the braids kind of have to go down always. So what it means is that we cannot have a trefoil or like any knots somewhere in between. So they look more or less like shown in this picture always. And it turns out that these two objects are related. So, okay. First so braids are objects in three-dimensional space, and it's kind of hard to think about them in this way always. So the observation here is to project them into a plane that passes through these two parallel lines. And we can move strings a little bit around so that we'll avoid these double crossings and overlappings additional, which will give us a valid braid diagram. And we'll use them further. Okay, so how these two concepts relate? Actually, we can obtain a link from a braid by closing it. So the procedure looks as follows. You just have to connect the opposite knots of a braid, and in this way you obtain a link. So it kind of looks like this. Okay. Now, why braids are interesting? Well, turns out that they have a really interesting group structure. And what is a braid group? We'll define it to be a group on n strands, and we'll consider braids under ambient isotopy under this equivalence relation. And the composition in the group will be just, you have to put two braids together. So you just kind of join one end of the first braid to the beginning of the second. And to discuss a little bit more the algebraic structure of braids, we'll need to introduce the following crossings. So sigma I and sigma I inverse, they will look like this. And if you you might notice that if you draw like these long sequences of crossings, then you might notice that there are some relations between them. So in fact, the following two are obviously equivalent, and you can just slide the crossings. And also, a little bit not so trivial, but still, you can move strings a little bit around and notice that the following relation holds. And it turns out that these are essentially all of the relations. Of course, you can combine them, but more or less, these are all of them. And that brings us to algebraic realization of this group. So this is called a Ray group, and it is the geometric Ray group that we discussed is isomorphic to a group with the following presentation. Okay, so now let's talk about the main problem that we will consider further. So we'll construct a random process in which we independently choose these crossings generators with some probabilities, and we'll just concatenate these braids, these crossings to form a braid. And some of the sequences of crossings will be prohibited. So for example, further in our random process, we'll see that we cannot have two crossings of the same type. And the question that we'll ask about them is, what is the limiting braid length expectation in this process? To make this a little bit more formal, we'll first talk about random walks on finite groups. So let S be just a set of symbols, and we'll consider a free group on it, and we'll define a word just to be some product of elements from S or its inverse. And we'll say that a group has presentation on R, that what we mean by this was just the quotient group of free group on S by the smallest normal subgroup that contains R. And what do we mean by length here? So a length is of an element in this group, in this presentation, is just the smallest positive integer R such that there is a word that represents G that is equal to it. Of course, there can be multiples of them, but we just care about the number. And what is interesting is that maybe it is a good idea to think about them in terms of picture, and Cayley graphs actually give us this picture of a presentation of a group. So this directed graph will be built as follows. So the vertices will be just elements of G, and we'll connect them whenever two elements differ by a generator or its inverse. Here are two examples. That's a Cayley graph of symmetric group on 3 elements, and of the dihedral group of a square, I think. Yeah. So here is also the definition of convergence and distribution. And for the sake of notation, we'll also introduce new random variables. So if we have random variable x, then f of x is just random variable which is built so that the probabilities will be preserved. So finally, let's construct a random walk on a finite group. It's just a Markov chain with state space G and transition probabilities that arise from this Cayley graph. So whenever we have an edge between A and B, the probability will be positive. If there is no edge, then it is 0. So further, we'll only consider diagonalizable probability distributions. So the matrix has to be diagonalizable. Why? Because it turns out that they have really nice structure in terms of that the limiting expectation that we'll have will be independent of the distribution in some sense. So it is given in the next theorem. So here we see that basically what it states is that given the structure of G, if we understand it well, and our diagonalizable distribution on it, then we understand that our group, our random variable, the limiting distribution of it. So it will be uniformal on some set of in G. And the immediate corollary of this proposition, of this theorem, is that if you take f and compute limiting expectation of f, then will be given by the following averages. Okay, we can immediately use this proposition for some simple examples. So for example, in cyclic case, we'll have the following expectations, limiting expectations based on what is M. And we can generalize this result a little bit to direct products of cyclic groups. So notice here that there will be always unique limits. And this proposition is useful because essentially, since any finite abelian group is product of cyclics, then we kind of know the limiting expectation for some presentation of any finite abelian group. Another important class of groups that we'll consider further to construct a braid group, a random walk on a braid group, is Coxeter group. So basically, it is a group that has the following presentation. And one simple example of Coxeter group, well-known example, is the symmetric group. So one can actually check that it can be presented in the following way. Okay. Related type of group is Artin-Sitzberg group. So given Coxeter group W, we can just get rid of quadratic relation sigma square is equal to 1. And in this way, we obtain Artin-Sitz braid group. So we've already seen an example of it in the beginning while I was talking about a braid group, like geometric braid group. So this is an Artin-Sitz braid group in type A. So there is a more geometric realization and related type of groups. These are finite reflection groups. So how do we define them? Suppose you have the Euclidean space and you have some vector and some set of vectors. And we'll define a reflection S alpha as some operator, which is non-identical, that fixes this plane, which is perpendicular to alpha. And yeah. And if we just generate from all of these reflections group, then this will be a finite reflection group, if it is finite, of course. And it turns out that, in fact, finite Coxeter groups and finite reflection groups are basically the same thing. Isomorphism. It is also interesting to ask a question, what are the invariants in this finite reflection groups? So we can consider symmetric algebra on a dual space and consider an action of our group on this algebra, on this K algebra, in the following way. And what is interesting is that every subalgebra of this K algebra, it is consists of V invariant polynomials. It is finally generated. So it was a theorem that was proved by Chivali, and in fact, it is generated by an algebraically independent polynomials. So why do we need this? So these polynomials are called basic invariant polynomials, and we'll denote their degrees by d1 and so on, dn. And their degrees turn out, even though there can be multiple sets of generators, so their degrees are unique to a group. Okay, let's finally define a random walk on a braid group. So notice that even though this group is infinite, we can still do that if we define the following mapping. So if we have a reduced expression for V, we'll define V tilde to be, essentially we just take V and send the corresponding generators to each other. So the question might arise why this map is even well defined, because there can be multiple reduced expressions. Well, this is answered by Matsumoto's theorem. And notice also that this function preserves length, and it enables us to define a random walk on Artin-Sitzberg group. Okay, and the main proposition. So what is the limited expectation in Artin-Sitzberg group? Except these two cases, we know that basically it is half of the maximal possible length in a group. So how do we prove this? First, we use the factorization of a point-correct polynomial in a group, in a Coxeter group, which looks as follows. Then we differentiate it with respect to t and evaluate it at 1. And that gives us formula for sum of length of all elements. And what do we do next? We'll need a table of basic invariant degrees polynomials for all irreducible Coxy groups. And also notice that, and also use the main classification of finite Coxy groups, and use the fact that whenever we take the direct product of two irreducible Coxy groups, we just, how do we find a set of degrees for these? We just take the union of both of them. So one has to notice that this union will be have at least two even numbers, even integers, always except these two cases, A1 and A2M, where M will be odd. So for other cases, we know that there are at least two even degrees. Okay, so let's denote them by di and dj, and notice that our if we evaluate this at -1, then both of them will vanish, these terms. And essentially, this finishes the proof. You just have to apply the main theorem that we, corollary of the main theorem that we discussed before that, and we'll be done. Okay. Let's also not forget about the exceptional case. So A1 is more or less trivial, but the dihedral case without M, well, it's not hard to see that, in fact, there are here there will be two distinct limits. So it doesn't satisfy the theorem. And also, I'd like to address one problem that I haven't mentioned. That's what we did, like the last proposition, it was about limiting expectation in Artin-Tisbury group. However, it is not geometric in a sense that geometrical realization for this, like for length in a geometrical break group, it holds only for type A, which we discussed like in the beginning of a presentation. For other types, well, it turns out that for type B, there is a realization geometrical for this random walk. And so how do we do this? We just have to, from Coxy group in type B, you have to lift them into so-called torus break group. So it is built in a very similar way. So you have n+1 strands, and one of them, so here it is marked with a blue color, one of them will be fixed. And if you consider the following like set of crossings, you might notice that these crossings, they satisfy relations from Artin-Tisbury group in type B. And in fact, it was proved that the group of geometrical group in this setting will be also isomorphic to Artin-Tisbury group in type B. And interestingly, if we close these braids, then you obtain links within the solid torus. So here, so this blue circle will be kind of an inner part of a torus, a whole, like. Now, another important proposition. So before that, we consider braids, but one can ask the question, what do we get if we close these braids? Can we say about something about them? And it turns out that we can. So in type A, if we close our braid in the random process that we defined before, we can find the limiting expectation of it. And it turns out it is given by nth harmonic number, Hn. So the main idea of the proof here is firstly to notice that the number of kinetic components of closure of V, it is just the number of cycles in a cycle decomposition of permutation. So here is a good picture to see that, in fact, there are two kinetic components, and this permutation, if you look at this permutation, then there are two cycles just. Okay, now since we know that, it just becomes, the problem is just to analyze the generating function for Stirling number. So it is given by the following, and essentially we do a very similar procedure to what we did in the last proposition. So we also differentiated and evaluated at -1, and basically this concludes the proof. So here we also need the fact that length of a permutation coincides with, have the same parity with n minus number of connected components. So let's also change a little bit the setting, and we'll construct a new random process in which we have, suppose we have a sequence of uniform, identically distributed random variables in this set. And now what we'll do is that we'll compose these braids so that any two of them commute. So we'll kind of put them in blocks. And we'll consider, the question that we'll ask is, what is, so we'll consider a new random variable which is equal to just sum of length of these. And the question that we'll ask, what is the probability of the occurrence of an event that this length is equal to some number. So we'll use largest deviations principle to solve this problem. And we'll answer it in the following proposition. So basically it says that this probability is given by the following entropy function, which looks as follows. And what is the main idea of the proof? Well, we just have to notice that the cases where this event occurs, the number of ways in which this event occurs, is equal to the number of restricted compositions of an integer into at most like some parts. And these number of restricted compositions, there is an asymptotics for this, which looks as follows. And essentially, it just all comes down to just cleverly, just some calculus that it's not hard to, in the end, not hard to get the asymptotics for this probability, which looks as follows. And if we substitute this this expression here, then the asymptotics will look like this with the entropy function given here. Okay, so I think this is it for my talk. Here are also the references. And thank you for your attention. If there are any questions, please ask.
Thank you very much. Please, questions, comments?
Okay, maybe I want to add a little bit. So when I was talking about realization in type A and type B, geometrical, so for other types, it becomes a little bit more difficult. As far as I know, in type D, there isn't a geometrical realization like that looks as in a similar way. So with similar construction of a break group. So we only know it for types A and B.
Mm-hmm.
Okay.
Okay. So if there are no any comments, then thank you again for your talk, and we will go have a 5 minutes break up to the next talk. let us continue our work today. And the last talk will be delivered by Nikita Skrypnyk from Richelieu Lyceum with the title Distribution of Characteristics of a Random Gaussian Diagram. Please, Nikita.
Okay, my name is Nikita Skrypnyk, and I'm from Richelieu Lyceum. As it was said, I'm very happy to be here. And firstly, I want to say that if you can't hear me, please say it, because I sometimes have problems with connection. Okay, today I want to talk about distribution of characteristics of a random Gaussian diagram. The main task is to study a special type of Gaussian diagram and the distribution of its characteristics. Firstly, let's give some definitions and then talk about the main topic. The node is a closed curve without self-intersections, and the flat diagram of the node is a projection of a node onto the plane. Gaussian diagram is a special method of representing nodes. A Gaussian diagram which corresponds to a plane diagram of the node is a diagram that consists of an orientated circle on which the preimages of the underpass and the transition for each intersection are connected by charts. Let's look at the example. On the figure 1, you can see the Gaussian diagram, and on the figure 2, you can see how the node which corresponds to Gaussian diagram of the node. Then the convey polynomial is a node invariant that describes the topological structure of a node or a link in polynomial form. The convey polynomial of a node is denoted by this rule. So every convey polynomial can be calculated by this rule, and the convey polynomial of the trivial node is equal to 1. Let's look at the example and calculate the convey polynomial of the link. Let's find convey polynomial of this diagram. We use this transformation, which was shown on the previous slide. So we get that the convey polynomial of this link is equal to the difference of convey polynomials of two trivial nodes. So convey polynomial of this link is equal to 0. Okay, let's return to the main task. We consider Gaussian diagrams of the special type. We divide the orientated circle into compartments, the parallel lines, and on opponent sides of the compartment, we place 3 points, which within the compartments are paired together by charts in a random manner. Each section of the diagram was obtained by connecting 2 random points from opposite ends of the section. You can see on the right side the example. This one on the top is made of 2 compartments, and this one is 1 compartment. Let's calculate the convey polynomial of the diagram. Firstly, we need to transform the Gaussian diagram to the flat diagram of the node, so we get the flat diagram which shown on the figure 2, and it's the trivial node, so the convey polynomial of this diagram is equal to 1. Let us consider the convey polynomials of all possible diagram of 1 compartment. So you can see all these convey polynomials in the table, and the images of Gaussian diagrams of these compartments. Now let's talk about lemma. The convey polynomial of the node with the chart diagram M is equal to the product of the convey polynomials of nodes with chart diagrams M1 and M2. Let's prove it. Let us use the method of mathematical induction on the minimal number of untied intersections. I'll describe what's this on the next slide. That there's more than one way to bring a node to a trivial one, but there's always a minimum number of steps that need to be taken. Let's look at the example so it will be more understandable what's minimal number of untied intersections. Let's take intersection 3 and intersection 4. So then we change each other the intersection 3 and the intersection 4. We both get trivial node. So the minimal number of untied intersection is equal to 1. So we can go different ways and get different numbers of nodes we need to untie, but the minimum here is 1 because it's after changing 3 and 4, it gets untied. So let's put k equal to 1, then this intersection is either in part M1 or in part M2 of the chart diagram of a node. Let it be in M1 for definiteness. Then diagram M2 corresponds to a trivial node and the equality holds. Let the statement be true for all k less or equal to n. Consider the case k equal to n plus 1. Let us choose one of the untangled intersections P of the diagram M. Let without loss of generality it be contained in the part M. Then by the properties of the convey polynomial we have the nodes M and so we got using that rule that was shown on the slide that convey polynomial, we get this changed one intersection. So we contain one less untangled intersection compared to the nodes M. So the introduction hypothesis applies to them. We get this. And substituting into 1, we obtain thus the mathematical expectation of the diagram is equal to the product of the mathematical expectations of the sections of its diagram. Let's look at the example. Mathematical expectation of this diagram is equal to the product of expectations of diagrams. Let us consider that the variance of the coefficients of obtained polynomial. We get it through the formula. Let's form the lemma. The variance of coefficients of the polynomial for a diagram consisting of 2 compartments. Polynomial is written in the general form here, so the distribution, so the variance of the coefficients is shown here. As the result, we get that there's no node that corresponds to the mathematical expectation of the node we study, but there's a node close to it. That's because there's variance that's not equal to 0. Also, using the corollary of Moivre-Laplace theorem, we got that probability of obtaining a node with a certain number of trefoils. So we studied the Gaussian diagram with 32 compartments, and we got the probability of getting number of trefoils which shown on the diagram. So from this diagram we can form the lemma. The Gaussian diagram of given type, which consists of 32 compartments, is corresponding to a combination of maximum 7 trefoils in the most cases. These are main references. Thank you for listening.
Okay, thank you very much for your talk. Maybe somebody have questions or comments, please. Let me make some short comment that as before in the talk of Georgy Zhylinskyi, we made here attempt to produce some family of random nodes or random rates and to count evolution of its characteristics. Also, it was expected initially that the so-called expected nodes will exist, but it occurs as Nikita shows that the expectation of the diagram is not related to any node because you see that corresponding Conway polynomial is not expectation of Conway polynomials is not a Conway polynomial. So we decided to look at the most probable nodes, and it was surprising that despite of the non-trivial structure, like Nikita shows that we can have 30 small parts of the diagram, which can be randomly chosen to have different structures. We have a sim structure. It looks like 7 trefoils, which is a multiplication of 7 trefoils. Also, it was, I must say that it was Nikita results about the lemma when we have Conway polynomials of the product of two nodes. It was interesting and not very easy to find and to prove. Okay, I hope to see next year to see a continuation of such investigation. Thank you again, and I must thank to all participants, first of all to all speakers of our 8th Skorokhod readings this year. Every participant will get the diploma of participation in this international conference. Also, I invite all participants, and you will get the corresponding letter, to submit paper about your investigation to our journal, Theory of Stochastic Processes. Of course, this paper will be reviewed before to be accepted, but at least we will be happy to have such papers. Thank all participants, and let me say that this is the end of the semester for our seminar Minialiyk Calculus and Applications. This is 29th year of our seminar, and next year we will have 30-year seminar. So please prepare your talk and send it to her. Send the title of the talk and abstract to Heorhii at August. Thanks everybody, and bye. Have a good summer.
Thank you.
Bye. Thank you.
Thank you. Bye.
Thank you. Bye.
Yeah.
Thank you.